So this is example number 4 for shear joints that are statically determined. Let's consider this case scenario, right? In this case scenario, actually, this is an example from your textbook. I modified it. You got all these dimensions, your edge distances, etc., etc. And you have a load F applied here and load F applied here. The whole joint is carrying F is equal to 85 pounds. That's what the problem says here. It gives you the type of uh, bolt that I'm going to be actually using here. This is the plate. I'm sorry. Uh, this is the plates, the two steel bar plates are that this is attached to, and then this is the plate. This is the bolt that the two bolts I will be using. You want the design factor 1.3. All this information is given, and you want to what will be your static recommendation for this joint. Um, so when I do this problem now, before I start, I need to find the material properties. So if you go to table 820, you can find that for this particular steel, this is your yield strength, this is your ultimate strength. For your bolt, going from table 8.9, this particular bolt gives you a proof strength of 85 psi, yield strength of 92 psi, ultimate tensile 120 psi, and then you do your shear strength. The shear strength for your plate, you can find when that information is not available, then just divide it by square root of 3. This seems to be a very good, this comes really from distortional energy theory and is widely used. So just divide by 3 and that gives you this value. And for the bolt, you want to use PS, proof strength in shear and your yield strength in shear. Remember, anytime you're working in shear, we should be using US, YS, and PS. These values are mainly when you're working in tension or bending, right? This is the diameter of the bolt that's given in the problem. You can see this is given here. Is a fine series and the grade 5, and then from the table I can find what my root area is, my tensile area is. Okay, so all this information I already got it from the tables. Now we can move it to solve the problem. So to solve the problem, what I have is I have loads. First of all, I need to find what loads I'm going to use in the problem. To do that, the first thing I know that F on my joint, acting at the joint, is I'm sorry, this is not pounds. Um, this should be kips. Okay, just make sure you fix that. It's kips. It's supposed to be kips. Um, okay, then when you do this, I have a design factor, a standard design factor 1.15, but the problem tells me I have to have a 1.30. So I need to multiply these two, and this gives me 1.50. That means that F I'm going to use for my analysis will be 1.50 multiplied by 85. That gives me a value of 127.5 kips. Okay, this is the load I need to make sure that my bearing is capable of carrying. Now, the load in the members, this is at the joint. This is load in the joint, load in the members, the steel members. Um, so we have upper and lower member. So you can see here, got upper member, I have a lower member. So if I did this, this will look something like this. Um, you got your bolt, and this has been applied. Then you have this. This is applied. You got a load there. You got another load there. So what you're going to have here is this is going to be F over 2, F over 2, and this is F. So therefore, the load in each one of these plates is going to be P is equal to F over 2, gives you a value of 63.75 kips. Okay. The loaded plate, this plate right here is 127.5 kips. Um, Now, the load acting in the fasteners, uh, so PS will be, there are two rows, if you would, you can see there are two rows perpendicular to F, 1 and 2. So this will be divided by 2, and this gives me 63.75 kips. Um, then PST, that would be the total number of fasteners that I have here. I have 1, 2, 3, 4. That would give me divided by 4, and that gives me 31.88 kips. Um, so now that I have all my loads, now I can go and start doing my failure checks. Okay, the first check I'm going to do is bearing stress. I need to make sure that my bearing is safe. So for my bearing stress, the first thing I do is calculate my area. Area used in the bearing is the thickness times the diameter. So the thickness is 1 inch. You can see in the problem. This is 1 inch. Um, and this is bearing stress of the loaded member. Um, 0.75 inches. This gives you 0.75 inches, uh, inches squared. So then your bearing stress will be your factor of safety times PS divided by AB. This will be 63.75 divided by 0.75. This is equal to 85 kips. So if I evaluate now my factor safety is sigma tensile yield. B, this is 54, this is 85, this gives me 0.644, less than 1. This member is not enough to carry this bearing load. I got two options. I can either redesign it or I need to increase the thickness. I need to increase the thickness of my member. Another alternative could be change the material to make it allowable. Although this does not satisfy our problem, let's continue with the analysis. Okay, and this should not be there. I'm sorry, since that was already included in the loads. Okay. So then the second case is the next section, uh, net section stress of the members. Um, so this AN of the loaded member will be W minus, and maybe you're wondering why I'm doing only the loaded, because I have the highest value of my load. The other one is P over 2, so it's going to have less load. So I know that probably this is going to fail first. But as a good check, you should be checking both, actually. Okay, so W, this is 4. You add all this, this gives you 4 minus 2 times this diameter. So this is 4 minus 0.75 minus 0.75, 2 diameters, and this gives you 2.5 inches. Then your next section check will be PS divided by AN. This gives you 63.75 divided by 2.5. This gives you 25.50 KSI. Um, you check your factor of safety and you find that sigma yield in tensile over sigma n, this gives you 2.2 2.12. This is bigger than 1. It does have uh, uh, net section capability. Okay. Now, if we check the edge shearing, so the available area in your problem, gamma is equal to E over D. Um, so if you look at your problem, is this distance over here? This is 1.5. The edge is calculated in the direction of the load. This is 1.5. So it will 1.5 divided by your diameter 0.75. This gives you 2 inches, which is acceptable. So your shear area that we will be using is 2 times uh, gamma was 2 minus 1 divided by 2, and this is 1 inch, and this is 0.75 inches. So the whole thing gives me 1.125 inches squared. So now I'm going to find what my shear strength is. Shear strength is PSTS divided by AS. That would give me 3188 divided by 1.125. Um, that gives me 28.33 KSI. And if I want my factor of safety, is yield strength. This is yield, don't forget. This is in shear yield, because I'm working with shear. Okay, and that would give me 1.110. Bigger than 1, I'm safe, I can move on. Okay, the next thing we want to check is bolts. So I'm going to check bearing in the bolt first. The bearing in the bolt is given by the following equation. TDS is 0.75 inches squared. Then your bearing capability, bearing stress will be sigma B is PS divided by ABS, and that gives you 85. So your factor of safety then is your proof strength divided by sigma B. This is 85 over 85. This is equal to 1. It barely has enough strength to carry, but it is still acceptable. Okay. So the next thing we want to do is, this is bearing check. Now we want to look at the strength. Okay. Strength, we will do first shear. There's no information if my bolt goes into the threads go into the members or not. I don't have the info. Since I don't have the info, I'm going to do the conservative approach, assume that my threads do go into the members. So in that case, if I didn't have the information, then I use the other equation. This is PSTAR, and I get a value of 90.82 KSI. You can find your factor of safety here. This will be PS in shear tau B. That gives you 0.54. This is less than 1. It cannot resist shear capability. You know it's not going to, it cannot do this, but let's keep on moving. We will redesign it later. So for now, axial load. In the case of axial, we don't have any preload. Uh, uh, there's no preload specified. So therefore, your problem actually is equal to sigma xx is equal to PB over AT. And this is going to actually equal to 0 because I don't have any preload. And when I don't have preloads, then the load in the bolt will be 0. Um, And note this, why? Because just remember this was equal to C applied. And when there is absolutely no preloading, then C is equal to 0. Then in that case, your P applied in your problem would be actually equal to 0. Okay, there's no actual loads in the problem. Um, the actual loads are a consequence of the preload. Uh, and if you just check your calculation here, obviously you're going to get 0 down here, so you get infinite, so it's not going to be an issue. Okay. Uh, the second thing we want to check is bending. To check bending, you can see that the maximum distance I have in the problem is 1.75. This is in the midplane of the plate. 1.75 is roughly here uh, in this direction. Uh, and then, so where am I? Um, it's right here. Okay, so it's this distance here is the mid plane to the third plate. Um, got one plate, you got the second plate, you got this one. This is the distance from here to the mid plate here. Okay, so that's why this is 1.75. The bending moment that I'm looking for is given by this equation times B, and that gives me 55.79 inches kips. Um, find your bending stress. 32 is 32 MB divided pi divided d square d cubed. You apply this give you this value. This is KSI, and factor of safety will be this is equal to 63. It's bigger than 1. That's not going to be an issue. So this is all we do in this analysis. However, remember, this is not what you really want to do. If you do this analysis separately, it looks like, oh, this is safe, but this was not safe. But look what's going to happen now. We want to actually use your ratios. Your ratios are tau B over SPS. This is the 1.47. RA is sigma XX axial. SP is equal to 0. RB is equal to sigma XX bending. SP, this is going to be 0.0158. So if I use the von Mises approach, gives you 1 divided by RA minus RB squared plus RA squared plus RB squared plus 3 times RS squared. All this gives you 0.68. This is less than 1. So this is, I need to redesign the bolt, or I need to figure something out. I need to add more bolts probably so I can redistribute the loads. Okay. Um, and then if you use the another factor, let's say if you use a more common factor that's used in the industry, let's say this one, you can see that this approach actually brings you closer to your failure mode. That's actually shear. So this captures much better. That's what it really is showing you. Okay, so in your problem, you can see that your problem really needs a redesign. So to redesign it, I'm going to go ahead and solve for what is the maximum capable load that your problem can have. And to do that, I'm going to use the worst factor safety I had. And the factor safety was given by this equation. This was the worst case scenario. You can see that was the lowest um, factor safety was 0.54. Here, I found that it was 0.64. So I just used the worst case scenario. And then from here, I solve for PST. I know this is 4, multiply 4 on both sides. And you can see that this is the maximum capability that my joint has. Okay, some recommendations that you could do is you could thicken your plate, you can change its plate material, you can choose a higher strength bolt that you're going to pay a big price, so maybe it's more heavy as well, and maybe a combination or recheck the whole configuration itself. So this concludes example number 4.